Okay, we are live. Hello, everyone, and welcome to ML Done, yet another exciting episode on MLOps and deep learning. So once again, we have Khalil here with us. Hi, Khalil.
Hey, hi everyone. It's good to be back here.
Great, great. So I think we're going to get our hands dirty with the data today. But before we get started, I just want to sort of have a very short review as to what happened the previous session. So if Khalil, you could just give us a sort of very short reminder of what we did in the previous session, then we can hop on that and continue.
Absolutely. So last week was really exciting. What we did was a follow-up to the week before, no surprise. And it involved setting up an environment, sort of a dev environment for GPU development. So essentially, we're setting a stage that would allow us to run PyTorch on a GPU, and then also have the same support for a non-GPU machine. We started off with a single environment.yaml file, and this would be a setting file that is used by Conda to create virtual environments. And then we went on to create an environment for GPU files, and then wrapped the two of them inside what we call a make file. So essentially having a single entry point into the process of creating virtual environments. It was really interesting. If you haven't seen it, please go back, have a look, just to make sure your environment is right where it needs to be. And then today, hopefully, Mehran will build on top of that.
Great, thank you so much. So yeah, so today we're gonna get started with the actual data that we will be using to train our variational autoencoder on. And as we discussed before, it's gonna be an image data because it's just exciting to generate people who don't exist, let's just put it that way, using our variational autoencoder. So without further ado, let me just share my screen. Right. So here, I'm just going to first talk about the data set. So a very sort of famous and popular data set website, let's just put it that way, out there is called Kaggle. So Kaggle is a sort of platform where you can have access to loads of different types of data sets, loads of different types of codes where people have actually tried to implement certain algorithms to do certain tasks on these data sets. And of course, we have exciting competitions on Kaggle as well. So Kaggle just, as you can see here on the left-hand side, they just announce different competitions, and you just define your machine learning algorithm, you train it with the data, and then you test it, you send them your test data, the performance of your model on the test data, and they'll let you know how well you did compared to other competitors. So it's definitely a website to explore for anybody who's interested in machine learning. Now, I'd like to draw your attention towards one of the very interesting data sets on Kaggle called Celeb Faces attribute, or Celeb A dataset. Now, when you go to a dataset page on Kaggle, you see different sections of it, like about the dataset, so the context, for example, or the content of the dataset. And some of them also describe how the data set was actually acquired and collected. So this is a data set of celebrity faces, like all of the different types of faces, different genders of people wearing different kind of costumes, having all sorts of facial complexion or whatever have you, like all sorts of different types of faces of celebrities. And if you go just down here, so this is the number of examples, like nearly 200,000 face images of various celebrities are here. So that's a decent size for training any deep learning model. We have nearly 10,000 unique identities. So what this means is you could have Brad Pitt in all sorts of, poses, having like 100, 200, 300 images in the data set, for example. We have 40 binary attribute annotations per image. I'll show you what this means. This is actually quite interesting. We're going to be using this sort of annotation file a lot. And this basically says whether a celebrity, for example, annotations are, this celebrity is bald, this celebrity is a male, this celebrity is old. So all of these labels are basically the annotations for that particular celebrity. And we have landmark locations. So in other words, these annotation files would allow you to define different types of tasks on this data set and train machine learning algorithms for different types of applications on these on this particular data set. And usually on Kaggle, you also have this sort of section where they tell you about all of the data files that you find in this folder, in one folder of this Celeb A data set. And so here you have a zip file, you have a CSV file, like different CSV files, 4 of them. I'm just going to give you an example as to what they are. We're going to visually see them, by the way, throughout our, analyzing the data. We'll go through each one of these CSV files and you visually see them. But sort of an overview. So we have a CSV file that basically splits the entire 200,000 images into, like, annotates them in terms of, like, this first chunk is for training, this middle chunk is for validation, and this last chunk is for test set. So that is just a recommended sort of split that the creators of the data set have come up with based on whatever metric they have. I'm not aware of how they've come up with this particular separation. We have bounding box celebration, bounding box celeb A, which is all about determining where the face is on an image. So you basically have the coordinates of let's say a point on the actual image, and also using the width and height annotation, you can actually extend that into a sort of a rectangle that is like a bounding box around the facial part of a celebrity's face. So this annotation can be used like for, face detection, for example, if you want to train a face detector, let's say. You have landmarks align celeb data set, CSV file. So it's all about image landmarks and their respective coordinates. So for example, you have coordinates of left eye, right eye, nose, and left side of the mouth and right side of the mouth. So the location of all of these parts. This is yet another annotation. Certain people might find it useful in their own application. It is available and I'm sure it's useful. And the last one that I think we will be using as well is a list of attributes for these celebrities, the one that I explained earlier, like around 40 attributes for each celebrity image. For example, are you bald or not? Are you wearing a hat or not? Are you male or woman, for example? So 40 of them. And one other thing that you need to notice is that sometimes under these data sets, we have the acknowledgement section, which means that if you're going to, in certain data sets, if you're going to use that data set and you're going to publish something, you have to, cite the creators of the data set, for example. So it's sort of a like copyright licensing thing. And down below, you have all sorts of, visualizations of different attributes for each image, but I don't want to get into this part because we're going to do the actual exciting part, which is actually coding and seeing what lies inside. So let's get rid of. Okay, Khalid, should I just close this, or do you have any comments on this?
Yeah, so do we need all files? I noticed there are some that have landmarks and some have annotations. I'm just kind of thinking towards the end of the end product here. Do we need, which CSV files do we need and which ones do we not need?
Yeah, at least right now, the way I'm looking at it is we're going to develop a variational autoencoder. Now, all that variational autoencoder needs to have, at least basically, is the actual raw images. That's all it needs. It's an unsupervised machine learning algorithm. So it just learns the distribution of the data and produces new data for us that doesn't exist in our data set. Now, of all of these guys, if we were to use any of them, I think this guy would be probably would have a higher chances of being used because, for example, our VAE, guys, by the way, variational autoencoder is also referred to as VAE, right?
Yeah.
So our VAE might get really good in producing, for example, celebrities with hats, but very bad with celebrities with eyes.
Okay.
Right? So we might be able to actually use this annotation to actually sort of filter out our training data into celebrities with different features and see which one our VAE does better on and which one our VAE does poor on, if that makes sense.
It does.
But, yeah. But other than that, these guys, I don't think they matter. Maybe this guy, like this, the train, validation, and test partitioning, maybe that would be a good idea to take this into account when we design an experiment. And that's it really. And this is the actual zip file with the actual images. Yeah.
Awesome. Okay, so I'm really excited to see what's contained in those files. So I'm certain that's what you intend to show, right?
Exactly. We're gonna look at the images. We're gonna look into those files. We're gonna get our hands dirty. Basically.
Let's do it. Let's do it. Can't wait.
Yeah. All right. So let me close this. So I've already downloaded the file. You can easily download it. It will take some time. It's like 1.3 gigabytes. And I've put it outside the repository folder simply because I thought that it might not be a good idea to push 1.3 gigabytes of data into GitHub, right?
You are correct. It's also that, I haven't read what's contained in the Kaggle page, but it's likely that we do not have the right to distribute it. So it's safer just to download it and have it somewhere centrally stored on your machine.
Yeah, good. So I called the right thing then. Okay, good. So then I go into the VAE repository that we've already cloned from GitHub, and this is, if you guys remember, this is the structure. And here under notebooks, I've created a notebook, a Jupyter notebook, and this is the extension of a Jupyter notebook, IPYNB. And the name is Exploratory Data Analysis, or EDA. Now, we have already installed IPython notebook, Jupyter notebook, so I should be able to open this. Now, the way to do that, like on Windows, you can easily go under the directory section and just go command line, CMD. That just opens your command line right. And how can I make this bigger? It's interesting. Control plus isn't working for some reason.
That's really weird. Yeah, I don't know.
That's okay. That's okay. So what we're not going to do much with this anyway. So we're going to activate our environment, right? So the environments that we have are these guys, and VAE is the one that we want to activate. So as we learned from Khalid previously, we can just write activate at the name of the environment. And there we go. We have VAE here. And this is where we should be able to go on Jupyter Notebook. And this is how you open Jupyter Notebook. Enter. It is a browser-based sort of, is that the right word? Application? Yeah.
Yeah, you're right.
Yeah, and it just opens the directory where I opened, where I actually opened my my Jupyter Notebook from, which is the directory of my notebook, and it doesn't show the .keep file because it's a hidden file. And I have to say that in on my screen, I mean, I think you guys don't see Khalid's face here because I'm presenting now, but I see his face. So every time I make any comments I'm not sure about when, he just nods along. I know I'm right. Okay.
Yeah, you're often right. So I think I'll be nodding a lot. Get used to it.
Good, good. So this is the file. We can just open it. You just click on it. Good. So it's a short file, right? It's a short file, and we're gonna go through all of these like cells. So we call each one of these rectangles a cell, right? This is a comment, or let's say markdown cell. This is a code cell. This is where you can actually code. And on the right hand side, you see that Python 3 is running. The way to run this, you just click on run, and this should run the cell, right? Now, some of these packages, I'm not sure, but maybe they're not installed. So we might have to actually install some packages. I'm not sure. Let me just, good. Actually, that was a good sign. So we don't have matplotlib installed, right? Matplotlib is what we're going to be using, the holy grail of, visualization. So that's a good sign. Let's just go back. So I'm just gonna first so this is a different command line, and you might wonder, why am I using a different command line or command prompt window? It's because the one that I was using is Jupyter Notebook is running on it. So I can't type right now unless I have to just close it or just exit from Jupyter Notebook. So that's why on a separate terminal window, I'm just going to activate my environment. And you notice that it doesn't matter that I'm not in the directory of my repository. It doesn't matter. It's just, you're just activating an environment. You can activate it from anywhere. So here is where we're going to install matplotlib. Now, typically, I usually, when I want to install a package, I just go, there's this website, PyPy, I think was the one. Yeah, this is my to-go one, but I don't know, Khalid, should I just use pip or should I just use conda?
I mean, it's good practice to use conda, but to be honest, it doesn't make a huge difference. It's likely that pip would be sufficient for what you have. And I think for the purpose of demonstration, feel free to use pip, and then we can inspect the differences going forward.
Okay, so if we wanted to change this to a conda installation, we can easily uninstall this and basically install conda version, right?
Exactly.
Good. Yeah, I'm a big fan of PyPy page. It usually has anything I want. It just, you see the command here, you just copy it. That's it. You just go to your command line. I right-clicked, by the way, it just pasted it, right? If I click enter, it should install this on VAE, on this environment. Good, good, good. Downloading all sorts of stuff. Khalid, if at any point you wanted to add anything, please feel free to jump in.
Yep, I'll keep that in mind. But yeah, it looks as if it's going well. So
good.
Let's see.
Okay, so we installed matplotlib. I'm just going to minimize this in case we need to come back and install some other package. So I'm not sure whether I need to restart this, but because we just installed a package under the VAE environment. But I'm just going to run this cell again. If we have installed this successfully and if the skeleton has been updated, it should just run smoothly. Okay, it ran smoothly, so everything up to here was okay. The other package that, guys, you will be using this a lot is pandas. Specifically, pandas has this sort of structure called data frames, where you can actually use data frames to load most of the time, the CSV files that you might have, data sets might come in all sorts of shapes and forms. They could be in form of CSV files. They could be, the annotations could be in form of CSV file, such as the CelebA data set. So if you're using machine learning, you definitely need pandas on board. Now, there's a notoriety with pandas that, okay, it's really, really slow and it's really annoying, but there are ways, like tedious and laborious ways, to make it faster by defining the types of variables explicitly to make them as short as possible volume-wise, but we're not going to get into it now. Let me just go ahead and install pandas. So if I'm going to go, that means pandas installed. Should I just go ahead with pandas page? Installing panda. You see, this is why I like PyPy.
Yes, so I think it doesn't make a huge difference. The fact that you've installed matplotlib using pip, I think we should use the same command, but this time pass in pandas to it. So
okay, so pip install pandas.
Yeah.
It should go well. So some requirements are satisfied already, like we already have NumPy. Now it's collecting packages, successfully installed. Good. I think we're good to go then. Let's just run this cell one more time. Good. So that little star that appeared just disappeared, which means that the cell has been run and it's all good to go. Now we're gonna see where we will use these packages. Okay, so don't worry if you haven't seen them before. Now, first things first is to load the data set. Like, one of the reasons we use this globe package, like from globe package, I'm importing a function called globe, and this is sort of a general approach that with using globe, you pass in a directory, right? And you specify, like for example here, the extension of the file that you're interested in with a star here. So this typically goes into this directory and looks at all of the files with JPG extension and generates all of the path directories to each one of these JPG files. So if you want to load any of these JPEG files, you have individual paths pointed to each one of them. So remember, in this website, in this data set, we have 200,000 images, right? So this should create 200,000 paths, basically. And then you can sort it. That would make it look nicer. Like if I ran this and I just print out what is inside this variable, this is what you see. So all of them share this chunk, except in the last chunk, they have the actual names of the data set, the actual names of the files. And if you want to sort of test it, remember, so this is the directory of my notebook, right? Let me sort of translate what's happening here. These 2 bits basically saying that go back twice. Like here, we're here, we go back once, and then we will go back twice. This is where we are. In here, we go into Celeb dataset folder, image align celeb folder, image align celeb again, and then we see all of the JPEG files. So this is exactly what's happening. So in this folder, you go here, you go into CelebA, and then again, and this is all of the images you have, right? And you notice that the actual names of the files start from 1 JPEG all the way to like 200 and something, 202,000, whatever images, right? So the number just increments. And for example, the directory to this first image, like the path towards this first image is using globe package is this. And you notice that it's a string. So the path is returned as a string, and all of the paths have been put into a list. So this line, remember, this line returns a list of path strings to each image separately, right? And you might wonder why we need this. This is going to make our life easier. So you'll see what I mean. So we go down, we can look at total number of images. So inside this list, we can just take the length of it and we can print out. This F is for format. This is the new way of, printing stuff with a, while converting, say, an integer value into a string. There's an older way of doing it, but this is the new, sort of a more, let's say, current way of doing it. But it's just a print statement, really. So you can confirm that the number of images is this. Now we would like to actually load these images. And when I say load images, for loading an image, you need the path towards that image, right? So I'm going to iterate through this list of paths, right, using a for loop. At each iteration, path becomes one of those strings, right? So I get that path string, right? I give it to the imrid functionality of matplotlib. Remember, we have imported matplotlib.pyplot as PLT. You see this line a lot. The subpackage of matplotlib that is called pyplot is what we use all the time for, generating all sorts of cool visualizations. So you can import this as whatever you want, right? Doesn't matter what it is. It's just general practice to put PLT. The same story goes here. Under matplotlib, we have this patches subpackage that we can import as whatever we want. We're just going to use the keyword patches. And you'll see where we're going to use this guy as well. But anyway, for visualization, we're going to use PLT to actually see those images. So we read the image, right? And it is also typical and sort of, good practice to, while you read an image, remember, an image is a matrix of values, to also normalize the image as you go on. Right? So these are regular RGB images whose pixel values range from 0 to 255. So upon reading each one of these images, I'm also dividing the actual raw values of those pixels by 255. Why do we normalize? Before I continue, Khalid, would you like to give your thought? I want to know whether you have an idea as to why we normalize.
I have zero ideas. My question, I was waiting for you to finish, but my question is, why divide by 255? What does the image matrix look like? So the line where you have plots.image read path, what does it look like? Why do we have 255 with a period after it? So like with a decimal point after it, why not just 255? So that line packs a lot, and I would like to know what's happening there.
Okay, sure. Good question. So I'm just going to create a new cell then. It's like a simple line. So in this list, I'm going to grab the first path. Before I even do that, let me just get even more detailed. So the first element in this list is a string, right? A path pointing to the first image. Now, if I want to read this image, I just put this guy here, right? I'm going to read this using this path. Now, if you want to look at what gets back out of this, look, this is just a NumPy array, actually, of values. And uint, they're actually integer values. That's interesting. And if I want to, let me just put this into a new variable. I want to just look at the dimensions of this image, look at the maximum value of pixels, minimum value of pixels, and so on and so forth. So first is so this is a NumPy array, right? So if I just put type image, it just types the type of this variable, which is a NumPy array. Now, if I want to look at the shape of the sky, all I need to do is print that shape. This is, again, a functionality of NumPy. When I do that, this is what I get. 280 by 170 by 3. So 1 is height, 1 is width. Do we know what this is? Any thoughts?
Depth, color.
So this is the channel. Basically determines how many channels you have. And you're right. So you have 3 channels, one for red, one for green, one for blue, RGB, right? So in other words, if I want to be more sort of accurate here, it's like, imagine this was 100, this was 100, this was 3. Now, if you want to look at the entire thing, it's like you have 100 by 100 image times 3, like you have one on top of the other on top of the other. One is about the redness of the picture, one is about the greenness of the picture, one is about the blueness of the picture. All together becomes one colorful picture that we see like here. For example, this image, if you look at it, there's not much blue going on. I mean, if I look at the blue channel of this image, it would be probably mostly zeros. Maybe green would be also zeros, but maybe red has more sort of values in the pixels, right?
Okay. Yeah.
So also it'd be interesting to see like what is the minimum and maximum pixel values of these images. Again, you can go. I'm a big fan of NumPy, so I just keep using NumPy. NumPy, like np.min, is like I'm calling the minimum functionality of NumPy, and it's awaiting a NumPy array. I'm just going to say, okay, this is my NumPy array. Across all of the pixels, across all of the channels of this image, give me the minimum value you see. It's 0. What about the max? The max value you see? 255. Right. So if we want to normalize these pixel values between 0 and 1, we can easily divide each pixel value by the maximum value, which is 255. But remember, it is not general practice. Like you can't just divide by the maximum number and expect that the result will be normalized between 2 certain values. There's an actual mathematical formula for this. If you want to normalize an image between the 2 values A and B, A can be -1, B can be +1. A can be 0, B can be 1. So whichever A and B you choose, there is a mathematical, it's a very simple mathematical formulation that allows you to convert the image into a normalized image. Now, again, why the trouble? Like, why do we bother with normalization? As we'll see later on, when we develop our artificial neural networks to do image generation using this data set, artificial neural nets work really well when it comes to normalized images. Again, you might ask why. I mean, the thing is, we can just keep going and going, but
all right, yeah.
but there is a very good reason why that's the case, and I'll show you exactly why that's the case. It has something to do with the activation of neurons. Like when the input value is small enough, around 0, the activation of that neuron has a higher chances of being like getting activated easier. But we'll get back to it.
Okay.
So this is just the decimal point is just to convert it into like floating points, really. No other reason. At least for now, it can just be 255. Without even I think this should be fine even without that. So yeah. So I hope that cleared out the story, Khalil?
Yes, it did. Yes, it did. Yeah.
Great, great. Good question. So here, what am I doing? Ignore this for a sec. So I'm going through each one of the path variables inside this list, and I want to read each image, normalize it between 0 and 1, and then show that image, right? By the way, don't think I cheated, okay? I'm gonna show you something. So if I were to normalize this guy between, like by dividing by 255, let's just see, does this really convert the pixel values between 0 and 1 or not? So if I divide it by 255, the min value should be 0.
0, yep.
Yeah. And the max should be
1.
Yeah, it should be 1. It might be lower than that, but it will never be higher than 1. Okay, it ended up being 1. But in some of the images, it might get to 0.9, 0.8, depending on the pixel values. Okay, good. So we read each image, and then we plot it, right? So because we have 200,000 images, I don't want this to go forever. So I'm just going to create, there are different ways of doing this. I'm just going to create a dummy value, let's say a dummy variable. So if counter, let's say bigger than, let's say 10, we will break out of this loop, right? If not, I'm gonna plot it. I'm gonna plot the image, but after I plotted the image, I'm gonna increment counter. So different ways you can do that. You can say counter equals counter plus 1, or counter plus equals 1. It says the same thing, right? So every time we plot something, we increase this. And once counter is bigger than 10, we break out of it. So in other words, we just want to plot 10 images in this data set. If I run this, first, oh, there's a reason why this happened. Because in Matplotlib, for some reason, I heard about the reason why this is the case. I don't know if you know, Khalil, but in Matplotlib, you need to explicitly mention plt.show so that it would consider a separate figure and not overwrite all the images together.
Yeah, I think it has some sort of buffer system in the sense that it's caching whatever image it renders, and then compiles them into a single bit. But if you want to flush that buffer, just like you do with file systems, you have to tell it to show. So what it does essentially is it picks all the images it has rendered in its own cache and then spits it out into your Jupyter Notebook, allowing it to create a new figure and start a new cache. So I think that's what happens behind the scene. It's been a while, but I normally this is how this plotting systems work.
Nice. Okay, that makes sense. If this guy like flushes that buffer, that definitely makes sense. So if I clicked on it, good. So first image, second image, third, fourth, we go down. I don't even recognize any of these guys. These are celebrities, right?
They are.
I don't know them.
Yeah, it's a massive data set with 200,000 faces. It's likely that depending on how familiar you are with Hollywood, and you know the music industry in America, it's very likely that you wouldn't know even 20% of them. I don't recognize either. Like I don't recognize anyone either.
I'm getting sort of like, am I too much of a nerd? Like,
no, you simply haven't consumed too many videos and too much music. Like if you watch a lot, you recognize them. I know that guy. I have no idea what his name is.
This guy.
Yep.
All right. Oh God. Okay. Anyway, so we programmatically looked into some of the images. Let's just put it that way. Now, we don't have to do it this way, right? But just to sort of as an excuse to be able to actually develop functions in Python as a refresher for those of you who might have sort of forgotten how functions are defined in Python. So just as a good practice, this is what I'm going to do here. Again, erasing that dot, we don't need it for the moment. So def, the name of the function you want, and the parameter that you want to pass. That's how you define a function, and everything else is indented one level in, right? So you say that, okay, whatever path I pass to this function, I'm going to read an image in that path, normalize it, and put it into this new variable, and I'm going to return this variable. So this guy loads an image and returns that image, whereas this guy receives an image and shows that image. So that's why I've named it visualize. Again, this is, you don't need to define a function for these guys, just a refresher. So when I run this, these functions have been defined. Now I can call these two functions, right? Good. Now here, I think, yeah, so we are actually going to, at this point, let me see, yeah. At this point, we're actually gonna load, let's say, for example, 500 images. We're gonna load them in memory. They're gonna be loaded in RAM, right? I'm gonna be loading them in an actual images list. And when I say loading them, I'm talking about loading the actual NumPy arrays of these images into a list, because I'm gonna do things with these 500 images. Now, I define a max number, say 500, and I put images as a list. You might wonder, why don't you load all of the images? Like, why don't you load 200,000? My computer just crashes when I do that. It's like, it requires so much memory that it just crashes. I know that Pandas has this mechanism of loading large volumes of data. I think it has some sort of a smart way of doing it, like slowly. I'm not sure if Khalil, you've heard of a remedy for fixing this issue.
I think there are many strategies to be able to load a lot of them into memory, but in most cases, it's sort of a trick. So like lazy loading. So what essentially does is internally, it keeps a pointer to each path. And whenever you try to display it, it now goes off in the background and then loads that image and displays it. And once that image is out of view, it takes it out of the memory. So in reality, packages like Dask, I think CD, Polars, these are all kind of extensions built either to supplant Pandas or to build on top of Pandas. What they do is they trick your operating system, or they trick Jupyter into thinking that all those files are loaded into memory. Now, if there are other strategies that rely on vanilla Pandas to load everything into memory, then I'm not aware of it, but I think it's entirely possible to do that.
All right, so maybe in the future, once we want to actually get started with training our variational autoencoder, maybe we would revise, or maybe sort of go back to this section and try and maybe we could come up with a trick to load all of it.
Oh yeah, absolutely. I think it's going to make for a very interesting case. I think, you know, not just for EDAs, but when you work with large data sets like we have at the moment, 220,000 or 200, just about 200,000, and then you have a small machine, memory is always going to be a constraint. So there are many tricks, and I think a very good machine learning engineer and a data scientist should be familiar with these tricks. So things like asynchronously loading data, the concepts of buffering and caching. But it's always good to start with sort of something simple like we have in this Jupyter notebook, and then eventually optimize, because, you know, done is better than perfect. Once you get to where you want to get to, you improve on that. So yeah. I really like this approach, plain and easy, simple, and brilliant. So let's go on.
Great. Yeah. Okay, that'll be very interesting, because I've never done that asynchronous loading, so it'd be cool to learn how to do that. So I'm defining a maximum number. Let's just put 100. This is just for sake of demonstration here. In a for loop, I'm using enumerate, sort of wrapping this guy in an enumerate keyword. Now this guy, what it does is, using this guy, you can not only enumerate, iterate through the data set while keeping track of the indices of individual elements, but you could also look at the actual values inside this list. right? So this is just a sort of keyword that you can use while iterating through data sets if you need the index and the value of a cell. Now, if index is smaller than the maximum value, I'll keep loading that particular path variable, right? The particular image, and I keep appending it to a list. And if it's not, I'm going to break. So this is to just make sure that we will load a maximum of 100 images into RAM, our RAM memory, into our images list, right? If I go that, if I run this, good. No errors. So images now, this guy, if you want to sort of verify, if I want to look at the len of images, we have 100 images here. And if you want to say plt.im show like one of the images, like say the 10th image inside this list, you can see it, right? So that was just to verify that we've done it right. So here's a nice piece of code where you can actually, we have 100 images. You want to be able to run the cell, and every time you run the cell, you would have 10 random celebrity images, right? Random. So that is why we have this chunk. Again, you notice that we are using NumPy a lot. It's a brilliant package. So numpy.random.randint, what this guy does, it generates random integer values for you. And you just pass in the number that you're interested in, like up to this number. That's how it works. For example, if I want to show you how it works as a small cell here, if I want to put 5, like say 3, if I want to put 10, right? So it will never exceed the value that you have put there. So it's always up to this number, right? And we're going to do this 10 times. So every time I'm going to be creating a new random variable, a new random value. And every time I do, this is going to be an index of that image inside images, right? And I create a subplot, which has 2 rows and 5 columns. And I'm going to use this guy here to actually name which part, like in which part of this grid am I going to put this image. And then I'm going to visualize this image again. So this is a simple function that we've coded here. Doesn't have to be a function really. You can just put this line down there. So it just visualizes your image. And that is why here I'm passing the actual index in the images list that refers to the particular and specific image that we want to visualize. Now, if I visualize that, if I run this code, okay, so you see a 2 by 10 sort of grid of celebrities, none of whom I know again, which is weird, but anyway. And you notice that I go I+1 every time. So that is why it first plots here, and then I increments to 1, and then it plots here, and then I becomes 2, it plots here. So that's how it just iterates through putting images in different parts of the grid, basically. Okay. Now, before we continue, first of all, if you guys have any questions, again, in the chat box, definitely let us know. We promise we'll get to them. And Khalid, if you have any comments, questions, please.
None now. It looks kind of brilliant. I'm wondering where this numbers on the X and Y axis came from. Is it by default? Does it have to do with the values in the matrix representing the images?
I don't know that. I mean, that was weird. Like, yeah. I usually, when I visualize images on a data set, I usually don't see numbers like that.
Yeah.
That was a strange one.
Because it does seem as if it goes from 0 to 200 and maybe 20 or something. I don't think that's up to 200 and. What's the maximum value in the matrix?
In the images?
Yeah, so for each image, the maximum value in its NumPy array would be 255.
So now it's going to be 1.
Now it's supposed to be 1, but then we have from 0 to 200. I have 0 ideas, but then this is something worth looking into. Maybe if we figure it out, we can post that on Discord. But yeah.
This actually, I think, a default of Matplotlib probably.
Possibly.
Or maybe with JPEG files, there is a protocol. I'm not sure. Like you have to specify your 0 somewhere. Like here, the center of coordinates is here, top left quadrant. Maybe that's just the way it is. Not sure, but one thing is for sure, and that's that this information is not hidden in the image anywhere. It's just a NumPy array. Doesn't have anything else. And like if you visualize each one of these images through your operating system, again, there's no such thing associated with it. I think that has something to do with Matplotlib, just doing it for you.
Yeah.
Which again comes in handy, as you'll see later on. So I run this, right? Good. Now we have gotten sort of comfortable with the actual images. The last thing I want to do is just look at the CSV files that we had here that we talked in the beginning of today's session. The CSV file. Now I'm just going to load each one of them and just have a little peek into what's inside. So we have 4 here, right? So first one is the list landmarks aligned celeb.csv. Again, I'm using pandas, and I'm using the very, very popular functionality of pandas called read CSV, right? It reads a CSV file, which is this guy. And what I'm doing here, I'm just considering up to the max num. Remember, I've loaded 100. I've loaded 100 images, right? So I'm just going to get the first 100 rows. Remember, it just increments, like each row is related to one of the images, and it just increments down one by one. So the first 100 rows correspond to information related to the first 100 images that we have loaded. And that is why here I have this chunk here. It means up to 100 rows, right? So this guy returns something that we call it data frame, and puts it into, I just literally chose the same name of the CSV file as the name of the variable. And if you want to look at what is inside that data frame, you can actually call the .head functionality of it. And if I run it, there you go. So this is called the data frame, and .head by default returns, I think like five rows apparently of a data frame. But if I don't want 5, if I want say 20, I can just put 20 and I can see the first 20 rows of it, right? Now let's just go into, just take a quick look as to what's inside here. So these are the coordinates, like the X coordinate of the left eye and the Y coordinate of the left eye. The X coordinate of the right eye, the Y coordinate of the right eye. The same for nose, for mouth, and that's it. So basically, where are the eyes, the nose, and the mouth? So, and on the left-hand side, you see the image ID, which is the name of the JPEG file. And this is where the coordinates of an image comes in handy. So if X is, for example, 100, so this is the X-axis, it's going to be around here, this axis. And if Y-axis, Y value is again 100, this would be the Y value. This would be around a point around here. So this could be, for example, representing the left eye of the celebrity, or like from her perspective, it's going to be left eye. From my perspective, it's going to be right eye. And so on and so forth. So this is an annotation file, guys. You can use this for object detection, for example, in the face, detecting eyes, mouth, and nose, right? So each one of these annotation files satisfy a different application that you could be interested in. The next one, the same 2 lines, I'm reading the same number of rows, but this time list attribute celebs.csv, Remember, so again, we have these CSV files that you download from Kaggle, right? So if I loaded this, again, another data frame. Now, for the first celebrity, right? For example, they're attractive. They have arched eyebrows, bags under eyes, they don't have. So if they have it, it's +1. If they don't have it, it's -1. And that's just how the creators of the data set have created this, created the data set. And it's nearly 40 columns or 40 attributes, right? Are they young? Yes. Now, for example, are they bold? No, they're not. So this is basically, you're talking about the image 00001. So that's this lady here. Certainly attractive, certainly not bold. Has more hair than me for sure. Doesn't have bags under her eyes, and so on and so forth, right? So this would be something that we might be able to actually use in the future to sort of create a more guided training set for training our variational autoencoder. It'd be interesting to see whether whether our VAE would be able to generate new celebrities, like bald celebrities or like women celebrities or not. That'd be interesting to see. The other one is list bounding box. So this is again this one is small, like the sort of top left hand corner of a rectangle. These are the coordinates, and this would be the width and the height. So you have a point on the image defined by x1 and y1. Using width and height, you sort of extend it into an actual rectangle. That is going to be a bounding box for the entire face of the celebrity. And the last part, which I think we'll be using it. This is the recommended sort of, what is it? Train, validation, and test split for this data set. Now, if I want to just show it really quickly, it'd be easier to show it here. List eval partition. Like if I open it on Excel, it's the same thing, by the way, only we're going to open it in Excel, right? You've got the image ID, you've got the partitions. Now you see zeros here. This is for the training. If I keep going, scrolling down, all of a sudden we hit ones. So these images have been left for validation. And if I keep scrolling down, we hit twos. These are recommended for testing the model, right? Okay, don't save. Good. Now, I just want to just sort of wrap it up with a couple more sort of cells here. One is, so this guy is a data frame now, right? That keeps track of, like, contains all of the attributes for all of the images, right? And what I'd like to do is, I'd like to get the image IDs inside this data frame for anybody who is wearing a hat. So in other words, go into this data frame, right? Look into the wearing hat column, which if I want to show you here, this is the data set, right? Wearing hats, yes, wearing hat column. Look into this guy, see where you have +1, means that they're wearing a hat, right? Now, this line extracts the row index of all of those guys who are wearing a hat. And if I put all of those indices into square brackets in front of, again, the name of the data frame, this guy, this whole chunk, returns the actual rows. Remember, these become the indices in the rows. This retrieves the actual rows corresponding to those indices. So this becomes an actual data frame. Of the entire data frame with all like 40 something number of columns that belong to people who are wearing hats, I'm going to just grab the column related to image IDs, and I'm going to convert that into a list. It's a long line, but this just shows you the power of pandas data frames. And then I'm going to look into what IDs I've retrieved, like these are image IDs. Good. So apparently we have 4 people who are wearing hats, right? Now, I'm going to use these IDs to actually visualize those images. This is just showing you how you can actually load your data in a more guided fashion. That's it. So I'm defined a dictionary here. Of course, there are many ways you can do it. This is just a fast sort of review as to how we can do it. Again, into the list of paths of all of the images that you have. You go in, right? And for each image, you go into all of the IDs that you've retrieved that belong to people who have hats, right? If the path that corresponds to a particular image in the entire data set, if that contains a particular ID, for example, contains this thing, then it means that this path is pointing to that very image who has a hat. Now, if that's the case, I'm going to load that image basically, and I'm going to put it into my images dictionary. And I'll show you what this images dictionary looks like. And then you might wonder, like, what is this guy? So that is just to make sure that we will not pass 100 images. And again, if we pass that 100 images, we have to break, right? Definitely not the most efficient way of doing it. There are definitely easier ways to do that, but that's just to sort of show you what's available here. Now, if I were to run this, now we have images dictionary loaded. Now, if I want to show you the images dictionary, what this is actually, you see the ID of an image as a key, and as the value for that key, you have an entire image. That's how it's been formed, right? So if I keep scrolling down, again, you'll have, for the next entry, you'll have another key, and then for the value for that key, you have, again, another NumPy array, right? So that's what a dictionary is. You have a bunch of pairs of keys and values. Let me just cut this. So for each key in this dictionary, I'm going to visualize the image corresponding to that key, right? So that is why I have dictionary, and then I pass the key value here. So images, the value corresponding to that key would be the actual NumPy array corresponding to that key in the dictionary, right? Then I called visualize function to visualize it, and I have plt.show to not sort of prevent overwriting images on top of the other. Now, if I run this, you see, they all have hats, right? Sorry?
Interesting.
Yeah. I mean, yeah, this is cool. This is really cool. Like, I mean, let's play with this a little bit. Like, if I were to put, what is it? Okay, here. If I were to put bald, right? Bald equal 1. Remember, guys, this bald, right? This has to replicate the exact column name here, because that's how you're filtering your data set. Now, if I go, yeah, bald here. So it has to be capital B, right? If I go capital B, where am I? Yeah. Bald. So give me the IDs of everybody who's bald. So there are 2 people, apparently. Now, if I were to, again, run the same, okay, good. We have 2 bald people here. Yeah.
Cool.
And the last chunk, again, this part is definitely not something that we're going to be needing, but just to show you what it means, the bounding box CSV file, right? So this is the data frame that contains the bounding box information. Now, I don't think I'm going to go through every detail of this code, because it's simply not something that we're going to be needing in this series, right? But suffice it to say that I'm going to, for every ID, I'm just going to grab the row corresponding to that ID in this data frame. Like if, for example, looking at the first row, I'm interested in retrieving this row, right? And getting x1, y1 width and height values out of it. And this is what this line is doing, right? And if I have this, first I need to load the corresponding image. Then I need to define a figure where I'm going to put the image on to demonstrate. And using Matplotlib's patches sort of a sub-package, you can actually pass in the coordinates of the top left-hand corner of a rectangle. Then you pass the width and height of that rectangle. So it extends it as much as the width, and it extends it as much as the height. So it all of a sudden becomes a rectangle. This is as opposed to having to pass 4 individual points. Well, this is easier. This is smarter. Edge color red, 4 color none, because you want to see the actual image behind the bounding box. And then you add the patch to it. So again, hopefully you'll have access to this notebook, and you'll see you can go through the code yourself as well. But this is just to show you how this thing is done. Now, you might notice that, like for these images, the bounding box seems to be like terrible. Like it just doesn't refer to the images. And it's simply because I did a little investigation, and I thought the code was wrong first, but apparently the data sets that we have on Kaggle, like this Syllabay data set, it's not the original data set. They have done some cropping around the images. So because of that, like the bounding boxes are tuned to the original data set rather than this data set. I wasn't able to find the original one. Honestly, didn't have time to go and keep digging the internet, like where's the first data set. But this is just to show you how you can sort of use bounding boxes to see where the face is. And then the actual coordinates of this bounding box, like you can consider it as an actual NumPy array. You can consider if your actual image is 100 by 100 and your bounding box is like here, right? You can consider an actual image the same size of your original image, but only with the elements that correspond to your bounding box being ones and every other pixel being 0. This is like a mask, basically. So you can pass in the actual image to an artificial neural network, for example, and ask the network to learn to produce the bounding box. So in other words, the network learns to detect where the face is because it's predicting the bounding box. So this is just a face detection sort of setup that you can use this annotation for. And yeah, I think that's it.
It's very interesting, very, very interesting. So knowing that the data about bounding boxes is incorrect, I don't suppose it will affect what we intend to do with the data set.
No, not at all. So this is just a CSV file that corresponds to the original images. The actual images are usable. Again, like all the variational autoencoder cares about is just gives me images with pixels. That's it.
Okay, nice. I'm thoroughly excited to see how we proceed from this stage.
Yeah, absolutely. So do you have any questions, Khalil, or any comments?
Not at the moment, not at the moment. I think this is very excellent. I think I've learned a thing or two about Matplotlib, especially with, loading images, viewing images, and then also creating patches. So yeah, that's very informative. And yeah.
Yeah, patches was an interesting one. I hadn't worked with patches before. That was an interesting one. Okay. So let me stop sharing. That was great. Thank you very much, folks, for being with us today. If you have any questions, please do make sure that you'll post them in the chat box or in the comment section of the video after we've uploaded it. Also, please do like, share, and subscribe to the channel. Hands down, that's the best way to support the channel so that we can sort of reach out to more people who might take benefit from this content or content such as this one. And again, thanks a lot to Khalil for being with us today. Khalil, I think this is rolling out to get into more exciting parts of the project.
Exactly. You know, dealing with images, I've worked with NLP in the past, but not a lot with images. And there's just a lot of details and nitty-gritties that are not familiar to me. For example, the concept of channels and whatnot. So, I like the speed at which we're moving. I really like the fact that everything is digestible and we seem to kind of move at a pace where it makes sense to me. Hopefully, it makes a lot of sense to the audience as well. So it's really exciting, Bob. I'm very, very thoroughly excited about what is this VAE and how does it magically do these transforms? If I'm trying to recreate an image or trying to spawn a new image of, inspiration from three other images, what happens if one is wearing a blue shirt, the other one is wearing a brown t-shirt, and the third one is wearing a vest? How does it magically just kind of create something out of nothing? So I'm excited to see what will happen in the next session.
Yeah, absolutely. I mean, one of the reasons, guys, that we chose VAEs, apart from the math that is useful for all of us to sort of learn, the other thing is some of the very exciting development, even recent developments in machine learning, are using some sort of autoencoding approach, like the famous diffusion models that right now everybody's talking about. It, you just pass a sentence to it and it just generates an amazing picture for you. It's based on autoencoders. It has a series of autoencoders inside of it, and more precisely, denoising autoencoders, if I want to be more precise. And if I want to even more precise, they're using units. So I mean, maybe that's something that we could sort of get our hands dirty with in the future. But the diffusion models are also very interesting. But personally, I mean, I'm just in love with the math of variational autoencoders. That is a math that you can use to understand. I mean, if you learn it properly, you can use it to a variety of techniques. In particular, if you guys are interested in the intersection of neuroscience and machine learning, for example, like how to model human perception in artificial neural networks, that is where the same math of variational autoencoders would come really handy to actually design machines that can perceive the world around them and can make decisions very similar to how our brain dictates those decisions. So it's an exciting math, and I can't wait to get started with it. That'd be really cool, actually.
Likewise, I'm looking forward to it.
Cheers. Okay, so if there are no questions, no comments, I think this is the end of our video today. So on behalf of ML Don, see you guys later.
Yep, take care. See ya. Bye.